All right, hello my friends. So in this series of videos, what I'm going to be doing is walking you through some of the basics of derivatives and partial derivatives. So in this class, we're going to be taking a lot of derivatives, but we're going to take the same derivatives over and over again. So the idea here is that if you're a little bit uncomfortable with this, we're going to spend a little bit of time going over the basic concept. Then we're going to walk through a general strategy for how to think about partial derivatives. And in the last video, I'm going to show you a couple of examples that are going to come up a lot, a couple of useful tools. So let's start with what a derivative is. And the basic idea here is, if we're thinking about a derivative or a partial derivative, what we want to know is how the output of some function changes when we change the inputs to that function, right? So let's take a really simple function. Let's say something like f of x equals x squared, yeah? So if we have a function like this, this is telling us essentially for every value of x, what's the value of f of x, right? So we could make a little table. We could say x versus f of x. Right, when x is 0, f of x is 0. When x is 1, f of x is 1. When x is 2, f of x is 4, etc., right? And if we wanted to, we could graph these things. So I could put x on the horizontal axis, f of x on the vertical axis, right? And I could say, let's see, 2, 3, 4, 5, 6, 7, 8, 9. Oh, all right, 10. And let's say 1, 2, 3, 4, 5. Right, so I could say that when x equals 1, f of x equals 1. When x equals 2, f of x equals 4. When x equals 3, f of x equals 9, right? So I'm going to have a little shape that's something like this. Yes? Okay, great. Now, if I want to think about the derivative, what I want to know, right, is how a change in x is going to change f of x. So for example, we could look and say that going from 0x to 1x is going to increase f of x by 1, right? Going from 1x to 2x is going to increase f of x by 3, right, etc. So this is going to tell us that the relationship between x and f of x, right, how much adding 1 to x adds to f of x, is going to depend on the amount of x we have. Now, when we're taking a derivative, what we're going to do is we're going to think about how a really, really small change in x is going to change f of x, right? We're going to think about essentially the rate of change at a particular value of x, right? So derivative of f of x with respect to x is going to be the rate of change in f of x for a tiny change in x at some value of x, right? Okay, great. So of course, in this case, right, we can take this derivative using our power rule. I'm not going to really talk through why this works, but I'm essentially going to say that the change in x squared with respect to x is going to be 2x. Okay, this makes sense? We're good so far? So this is what's happening when we have a normal derivative, right? A derivative with a single valued function, a single variable in the function. Now when we think about a partial derivative, what we're going to be doing is we're going to be thinking about a problem where instead of having a single variable, we're going to have multiple variables that affect the value of some function, right? So let's say we've got something like f of xy equals y times x squared. This make sense? So different values of y are going to give us different relationships between f of xy and x, right? So for example, I could say if y was equal to 1, right, I could say f of x and 1 is going to be 1 times x squared, right? F of x and 2 is going to be 2 times x squared. Okay, so far so good? So we can do the same thing, right? We can have values of x. I'm going to have values of f of x and 1, and values of f of x and 2. Great. So, right, if I evaluate x, f of x1 and f of x2, it's 0. Let's just stick with f of x1. Right, I could say that if x equals 1, then 1 times x squared is 0. Or 0. If x equals 1, then 1 times 1 squared is going to be 1. Right, if x is 2, then 1 times 2 squared is going to be 4. If x is 3, then 1 times 3 squared is going to be 9. Yes? And then our blue function, right, where y is equal to 2, we're going to have 0, 2, 8, and 18. Right, because this is going to be 2 times 1 squared is 2. Right, 2 times 2 squared is going to be 2 times 4 is 8. 2 times 3 squared is going to be 2 times 9 is 18. Okay, this makes sense? So if we're going to graph this now, what we would have right is something like this. Where if we graph first the value of the function when y equals 1, right, it's going to have a value of 1 when x is 1. It's going to have a value of 4 when x is 2. It's going to have a value of 9 when x is 3. Like this, right? This is going to be f of x and 1. And when we graph the function when y equals 2, we're going to say that when x is 1 and y is 2, the function is going to have a value of 2. Right? When y is 2 and x is 2, it's going to have a value of 8. When x is 3 and y is 2, it's going to have a value of 18. Okay. So the reason that I'm doing this, and the reason that I wanted to show you this, is that if we look at these two graphs, it's clear that the rate of change in the value of f of x depends on y. Right? If we think about the change from x equals 1 to x equals 2, well, when y has a value of 1, the rate of change there is going to be plus 3, right? F of x is going to go from 1 to 4. But when y has a value of 2, the rate of change, or the amount of change, is going to be a 1 unit increase in x, increased f of x from 2 to 8, right? So it's going to be plus 6. This makes sense? So we can see that the relationship between x and f of x depends on y. So when we're taking a partial derivative, what we're doing is essentially we're asking how a change in x affects the value of f of x for some given value of y, right? What we're thinking about is essentially what happens as we move along these curves that we could draw for any particular value of the other variables, right? In this case of y. And so we could do this pretty easily, right, using our standard derivative tools for a specific value of y, right, for a value like 1 or like 2. But what we're going to want to do when we take a partial derivative is we're going to want to think about how this is going to work for any given value of y. Okay, so with that, I'm going to talk through, in the next video, I'm going to talk through how we might actually do that.